Bismillah ar-Rahman ar-Rahim. So today we're going to start a routing layer in mesh networks. So we'll talk first about the unicast routing, and then we'll touch a little bit on multicast and broadcast routing. So at the beginning, what is the definition of the routing problem? The definition is that you are given a network which can be represented using a graph. So you have a graph that represents, this is the easiest thing to model a network. You convert it to a graph, okay? So each node has, each node or each vertex or each point in this graph has a unique identifier on an IP address. And the goal of the routing problem is just you have to derive a mechanism that allows a packet or a complete path to be established from one node which represents the source node to a destination node, such that the end-to-end cost is minimum. Okay. So of course, if you get out of your house and you start to drive towards the university, there are multiple ways to get to the university. One straightforward mechanism is just to select the shortest path based on the distance, and that's it. But of course, that might not be the best path, because if you have an intersection with a lot of constructions and stuff, then this intersection is congested, in which case this is not the best path. So you have to define new matrix in order to find on each road or each street, how do you define the quality of that street in terms of, is it loaded, is it not loaded, is it good to be part of the end-to-end path or not? So there is the routing and forwarding problem. The difference between routing and forwarding, what is the difference between routing and forwarding? Routing, we're talking about an end-to-end path, which means that you have the full picture. Forwarding problem means that at this point in time, I have a node here that's connected with multiple nodes. Okay, so we don't have the global picture how to get to the destination, but this node has to take an initial local decision. Should I forward the packet to here or here or here, without having the global picture? That's the difference between routing and forwarding. So forwarding here talks about the fact that in this simple hub, how do I forward the packet? Routing talks about the fact that I want to send to this destination. What is the best node that takes me to that destination? So it's based on knowing the end-to-end path. So routing here uses a data structure, which is what we call table or a cache. So each node has a simple table here, which lists all the possible destinations in the network, and then it says to forward any packet, the node will ask itself which destination I should get to, and from that destination I know what the next hub is. Okay, I need to do the forwarding to this node or this node or this node based on routing table. This routing table has to be generated using the routing protocol or the routing mechanism. So the routing protocol or the routing mechanism will allow you to create this routing table, which tells you if you want to go to this destination, you need to go this way. If you want to get to another destination here, then you have to possibly go this way, and so on. So this is routing, forwarding, and how we perform routing through routing table or a data structure that stores the destinations and the next hub. So the forwarding process is done by consulting these data structures. So if I don't have this data structure, I will take the forwarding decision based on no knowledge, in which case I have to just guess and take one of these forwarding nodes, okay, or forwarding path. But usually what happens is that the forwarding process consults the routing table in order to forward the packet in a specific direction. Okay, so forwarding is just a one-hop process, but routing is an end-to-end process. Okay, so do you know the difference between the two? I'm asking. Do you know the difference between the two? Okay. So the challenge. Well, the challenge now is that how do we define the optimal end-to-end path? Okay, so based on the example that I just mentioned, if you go from your house and take the road to the university, then you just guess and say, okay, I'm gonna take this road and this road and this road. Based on your knowledge, what is the shortest path? The shortest path might not be the fastest path. Okay? So in order to find the best path, we need to define a metric. And this metric defines the cost you have to pay in order to go on this link, or in our example, to drive in this street. So to drive in this street, what is the cost you have to pay? Okay? And then based on this cost, you calculate the end-to-end cost, which could be simply the summation of all the costs on the individual path. And based on that, you say, okay, in order to reach to that destination, I need to go this way because this is part of the shortest or the fastest path. So the optimization matrix here is somewhat heuristic in the sense that I can define this cost in any way. I can define it based on probabilities. I can define it based on time, the time I take to go past this street, or the probability that there is no, for example, construction in this street. So I can define my metric in multiple ways. Okay, based on that, we can perform the routing end to end. We'll see. So based on these definitions, the basic definition of routing, the main question is, when do I have to start performing the routing process end to end? Well, by routing process here, we mean that we need to find what is the best path end to end. Okay? And the way for us to find what is the best path is that possibly we have to try something. We have to send a packet, okay, and maybe calculate what is the end-to-end time that this packet takes in order to reach to the destination through different paths, and then find the path, the single path that can allow the packet to reach to the destination in the shortest time possible. So I have to try. I don't know if I would not know, I would not have an accurate estimate end to end until I try myself at least once, or at least get some idea about the time that I take in each individual hub. Okay? So the question is now, when do I have to do that process, that procedure, to try to calculate, to estimate the quality or the metric on each street or each link? When do I have to do that? We have 2 or 3 approaches. The first approach is that I have to be proactive. So normally I have I have a network, and then there is a source here that tries to send a packet to the destination. Now there is a traffic that needs to go from here to here. Okay? So the packets will be buffered in this source and will wait for an end-to-end route to be established before it sends the packets. Right? So before sending the packets from this source, I need to know where to forward it. Okay? So we said that we need to consult the table, but we need to establish the table in the first place. We need to generate this table. So at the beginning, there's no table. So what do I do? Well, one approach, we can say, let's just always, all the time, send some probe packets between this source and all the possible forwarding nodes, which means that this source will send like some broadcast probes. Probes are not data packets. These probes will help just estimate the quality on each link. Okay? It's like you're sending fictitious cars in the streets just to be able to estimate the condition of that link. How does it look like?
This is done only once in the beginning?
That's the question now. This is the question that we want to answer here. Well, the first option, it turns out the first option, it does that all the time, constantly. Because guess what? We have to be proactive. I don't want to wait. If this node wants to send packets, I will not say, okay, look, please wait until I establish the end-to-end route. Because this waiting might be maybe 10 seconds or something, which affects the quality of service of the application. Because the packets are going to stay here for maybe a long time. We don't know until the end-to-end path is established. This is the second option. But the first option is to say, let's just be proactive. Before I get any demand to route packets from a source to a destination, I'm going to be proactive. The routing protocol in the network will keep discovering all the neighbors and will keep estimating the quality of the link, even if there is no traffic demand. So we call that a proactive routing protocol. Proactive means
it will keep doing
it will keep doing that all the time.
Isn't that costly for the network?
Of course, there is a big overhead. There is a huge overhead. But guess what? In some cases, especially in wireless, there's no escape around this. Why? In wired, this is crazy. You cannot do that. You just cannot do that. Okay? People have done this in the beginning, in the early, days of routing, which is RIP, or Routing Information Protocol. But after that, they realized that this is crazy. We cannot just send periodic updates every time, because the state of the links that do not change, especially in wired. The state of the links do not change. So the chance of changing the state of the link after you establish it at the beginning is very low. However, in wireless, that's not the case.
So are they doing this because they assume that the nodes are dynamically changing?
Exactly. So in wireless, let's talk about the source of dynamics in wireless. Well, on one hand, this wireless link, the condition for it changes, right? It changes, maybe it changes every second. Because the channel here, you get some obstacles, you get some interference, all sorts of uncertainty on the link. Right? What is another source of dynamics here? Mobility. Mobility is another problem, especially in mesh networks or in ad hoc networks. If these nodes move, the whole topology of the network changes, which increases the dynamics on this link.
But this sensing for the links made by each node, so it can
Yes, of course.
but it can broadcast the.
It has to.
So each node can sense only one hop.
Yes. No, not one hop. It sends all these links. Yes. Through broadcast probes.
Through one hop, not all the.
No, not all. No, not everything. Well, I should say it depends. It depends on the type of the routing protocol, which we will talk about. It depends on the routing protocol itself. Okay. So depending on how proactive you want to be, the overhead may be prohibitive. It's a lot. But in some cases, you know what? I mean, you cannot do anything about it. You just have to go through that. Especially if the network is so dynamic and nodes are moving and stuff. That's the only way. You have no way around this. Option 2 is the other extreme. It's only on demand. So if you have packets to send, you keep these packets waiting, you establish the route end to end, you send these packets, and when the session dies, this route dies. That's it. If another session comes in, you wait, create the end-to-end route, packets are done, route is gone. That's it. You start a new session end-to-end and so on. So this is the other extreme, on demand. Of course, the overhead here is 0, but the performance is not guaranteed. Here, you're not affected by node mobility that much, but you have to establish this route every single time you want to send traffic. Okay? So that's the other extreme. The third option is a combination of both. We say that, well, I have to say that for option 1, when you send these probes back and forth, this will help you to generate the routing table, right? You keep exchanging these probes back and forth, and then update your routing table, right? Here, there's no routing table. I don't need to have a routing table because the route gets established only when I need. So when I establish a session end-to-end, the route gets established. Each node knows exactly that this session is going, so I need to forward the packet to this particular node. That's it. Once this session dies, this whole route dies. Okay? There's no routing table here. In this option, there's no routing table.
By the node, by the packets, so like every time you need to send a packet, it will look for a route.
Not for a single packet,
Then.
or for a group, a session of packets. Like an application wants to send, for example, a file. It chops the file into packets, and then it asks the source, I want to send all the packets belonging to this file. So the routing protocol in that node will be triggered, so and it will say, okay, wait, I will establish the route end-to-end, send all the packets, gone.
Is this like a user on a computer clicking a link?
Yes.
Then you have to do all of this?
Yes.
Every time?
Every single time, yes. Yes.
I guess that's not efficient.
Well, that's not efficient, of course. So for every single, so we call it a session. If a user clicks, or if a user wants to have a content of a web page or something, then the server will send this content in packets, and once the content reaches the receiver, then this session is gone. Okay, that's that's one session. So during this session, the route will be established end to end. Once the session is gone, the route established end to end is gone. Okay. So this is the second extreme. The third extreme, the third option tries to get a combination of both. It says, okay, so I will establish the route on demand. However, there is no point that when these packets are gone, that I should remove the route. Maybe I need it in the future, so I will keep it in the routing table at least for some time. Okay, so this will allow it to say, okay, so now I want to let's say that we have a network here. So I want to send from this source to this destination, for example. So I will start performing the routing, and we'll see now how the routing protocols work. So the route ended up being like this. Let's see. Okay. This means that this node will have a routing table with this forwarding path, that if I want to send to this destination, I need to send through this node. This node as well will have a small routing table that will have, let's say that this node is 1, this node is 2, this node is 3. Okay, so the source will have something like this. This source will have D. If I want to send to D, I need to send to node 1. It will have an entry like this. If I have a packet and I want to send it to D, I should forward it to 1. That's what this means. This node will have an entry that says D 2. Okay, this node will have a routing table that says D3, and so on. Sorry, the pen is not helping. See the. So anyway, so these entries will, and this node will have D and D. So if I want to send to D, just forward it to D because D is directly connected. So that's how the route is established end to end, right? So once this route is established, I will keep these routing entries in the tables. So later on, there is a source here that wants to send to D. There is a source 2 wants to send to D. Okay? So in that case, maybe the routing will become, the routing will end up being like this and like this. Okay, so in that case, this part I don't have to establish it, it's already established, but I have to establish this part. Right? Why? Because this part was established from the first time. So I only need to discover this part. Once it reaches to that node, this node will say, okay, if I want to send to D, I need to send to 3. So it will consult the routing table. It will find that it has a route to D through node 3. So this part will have to be discovered, and we'll see how. We'll have to discover it. But this part will not have to be discovered. Why? Because it was discovered from the previous session. So this way I can save some time. I will have to establish this part. I don't have to establish this part. Right? Because this part was established from the previous time.
But you're assuming that they didn't move.
Yes, of course. Yeah, we'll talk about that. Yes, of course. assuming that everything's fixed. But if they move, that's another story. That's a good point. Okay? So this is a combination of, or hybrid option. So we have to do some discovery for part of the route, but because we do not have to clear the cache for every single session, we keep the cache for some time. Okay? Not all the time. So these entries in the cache, they expire after some time to facilitate the fact that nodes are moving. Okay? So in that case, part of the route end to end will be very fast because it's already established from previous time. It's a combination between the two. So we'll talk about 3 different examples, one in each category. We'll talk about one routing protocol, a specific routing protocol for each of these categories, or each of these 3 options. The first option is what we call destination sequence distant vector. By distant vector here, we mean that we have a big network, okay? And in order for me to reach from a source to a destination, now we want to discover the end-to-end path. That's the job of the routing protocol, is to tell you what is the best path, end-to-end. Okay? So the way that distant vector routing protocols work is by saying, my decision is gonna be greedy, in the sense that when this node receives some probes from all the neighboring nodes, okay, it will calculate the distance and basically says, I'm gonna take the one that leads to minimum distance, minimum accumulated distance. So this node will say, when you, so what happens is that you start sending probes, and these probes will have to go through distances like this. So for example, when this node sends the probes, it will have to go this way and this way and this way. Okay? So this node will be able to calculate the distance from here, and this node will be able to calculate the distance. For a particular node, it receives the distance from here and from here and from here, right? And this distance is gonna be an accumulated distance. So the node simply says, I'm going to select the path that gives me the minimum distance, the minimum accumulated distance. And that's what we mean by distance. Distant vector is the fact that this node will say, okay, I'm gonna select the node that gives me the minimum distance based on greedy decision.
You said earlier that minimum distance doesn't mean minimum.
Of course, whatever that distance is defined, however that distance is defined, it could be simply number of hops. We'll talk about that. It could be a number of hops, or it could be the distance geographically, or it could be the quality of this link, and we'll talk about many ways of estimating the quality of the link. Whatever that distance is, at the end we have a number on this link, number x here, that defines the cost or the distance of this particular link. So this node, when it receives multiple probes from these multiple links, it will take the forwarding node that gives it the minimum distance based on greedy decision. This algorithm is what we call Bellman-Ford algorithm. Bellman-Ford algorithm. Okay, so this algorithm is actually is distributed. Why is it distributed? Because the when you send the probes from one node to another, okay, this node will calculate the distance between it and the source. And then based on that, it calculates the minimum distance between it and the source. Then it forms a vector of distances. And then it takes this vector of distances and it sends it to the next one in a distributed way, irrespective of the distance sent from the previous nodes. So each node will send its distance vector independently from any other nodes. Okay? So each node will collect distance, vector of distances, and will send it to all the other nodes. When this node receives the distant vector, it will ask itself, do I have a route to this node better than what I have in this table? If the answer is yes, then I will update my table with the incoming distance. If the answer is no, then I keep what I have in the table and move on. Okay, so that's why it's distributed, and it's asynchronous in the sense that these updates get sent asynchronously. They don't have to be synchronized in any way. It's totally distributed. And the algorithm is very simple. I have an incoming distance to a particular node. Is the incoming distance better than what I have? If the answer is yes, put it. Update my table with the incoming distance. If the answer is no, then leave it, move on. That's it. Okay, so it's very simple, distributed, very simple, and it's in a way scalable. But it requires the fact that you have to send these updates periodically and regularly. You have to. This is the condition now. You have to keep sending these updates regularly. Is there a way to enhance it a little bit? Yes. So ideally, the Bellman-Ford algorithm here, so it's based on Bellman-Ford algorithm, which is distributed. Bellman-Ford is good in the sense that it's distributed, it's based on vector of distances, nodes sent to each other, then following nodes will ask themselves, do I have a better route? Yes, leave it. If the what's in the distant vector better than what I have in the table, then update my table, and that's it. So it's very simple, but the condition here is that it requires some regular updates. So this distant vector routing protocol has been existing in wired networks for quite some time now. Okay, so there's nothing new. Conceptually, there is nothing new. Bellman-Ford has been used in distant vector routing protocols like RIP, like IGRP or EIGRP, and this has been running for wired network for decades. So there's no problem with that. What's different in wireless now, and particularly in wireless mesh networks or wireless ad hoc networks? Well, the difference is that nodes might move. The cost on the links might change, in which case the best route now might not be the best route after 2-3 minutes, right? So that's why being proactive will help here, because if we send these regular updates every now and then, with the fact that the cost of the links change, we'll be able to get what is the best end-to-end path at any point in time. So as the nodes change, the cost on the link change as the links are dynamically changing. The cost on the link will change. The probes will pick up the new cost, will send it to all the other nodes. All the other nodes will ask themselves, do I have a better route, better than what's in the probe? If the answer is no, then I take what in the probe and I put it. And I do that proactively, I do that regularly, so I'll be able to adjust and adapt myself to every change. Okay? So the distant vector, they exchange this probes, or we call it routing messages. Routing messages are separate and different from the traffic. These routing messages will have to be exchanged regularly, proactively, regardless whether I have traffic or not. And the good thing about that is that I will form the routing tables, and my routing table will always be updated. So whenever I have a demand to send traffic from any node to any node in the network, the nodes will know how to route it. خلاص. It's like you go to any intersection in the street, and the intersection will tell you, go this way if you want to go to the university. Go this way if you want to go to Al Khalifa roundabout. Go this way if you want to go to this. So you have signs that tells you, if you want to go to this particular destination, you better go this way, or you better go this way. So that's what the routing protocol in each node will do. Okay? So periodically we'll have to send all the full route updates. And that's, of course, very expensive in terms of overhead. So even in the wired networks, some enhancement that could be done is by saying, okay, I will exchange once the network starts up, without any traffic updates. Once the network starts, I'm gonna exchange these route messages until some saturation condition happens or steady state happens. What is the steady state? The steady state happens when all nodes find all the distant vectors, okay, have no absolute new information other than what I have in the table. Okay, so when the network first starts, all the nodes will exchange these route messages until the nodes come to a situation that it says all the incoming route messages do not have any new information for me, which means that my table is up to date, is updated with everything. I don't need any new information, which means that your network, the network is stable, it's fixed, and the condition is fixed, and that's it. Okay? So when I reach this state, I can then say, stop exchanging the routing messages to optimize the overhead, to reduce the overhead. And if there is a change in the network, the node that's affected by this change will trigger a new route update. So for example, this is just an enhancement to this routing protocol. So we have a network. Okay, and then this is the best route. This node moves. This node starts to move. This node will sort of detect the quality on this link, and will sort of get some idea that this link is becoming unavailable, or has become already unavailable. So only then this node will start sending route updates or message updates to all the nodes to trigger the process of sending routing messages again. But after steady state, all the nodes do not send unless there is a network change. In wired network, this could be, the change happens, of course, less often, because the change basically happens if you change the topology. One of the routers go down. It goes down. It's turned off, or there is a complete failure, or a link goes down. Someone actually took up the wire physically. Of course, this change happens less often, but it may happen. In that case, the node that gets affected by this change, it triggers the route update. So instead of using periodic updates, the periodic updates run for the first 2-3 minutes until you reach steady state, and then you switch to what we call triggered updates. Triggered updates, okay? So this way we can save a lot of overhead for this type of routing protocols. So any question about this? So in order to improve the performance in that case, we can use triggered updates to minimize the overhead. Okay, but initially this protocol is proactive, which means that by default it uses periodic updates, which is expensive. For the case of reactive protocols only establish the route on demand. So initially there is no information. I don't have to exchange route updates regularly. I don't have to do anything at the beginning. Only when there is a traffic demand, I will say, okay, let's just discover a route to the destination. Yani the source is saying, I want to send some packets to this destination. So here, the routing protocol DSR will say, I want at this point in time to discover a route to this destination. How? How do we do that?
Well,
I got out of my house. I want to go to Sea Lion Beach. I have no prior information. Where is this? What do I do?
it doesn't have the data table.
It doesn't have routing table. No. Because it's not proactive. It doesn't exchange any routing messages. The routing table gets established if I exchange routing messages. I did not do that. And I don't want to do this because I don't want to be proactive. I want to be reactive. How do I do this?
So then it looks for a route on demand.
On demand, yes. How do I do that? I keep the packets here.
Try and update. Send and update.
Trial and error. What do I do? Try and error. Okay? Either I say, okay, I want to get to Sea Lion Beach Resort. Okay, so let's move this, and then here, and then here, and then here, and then here, and see if I reach. I didn't reach after quite some time. Okay, so maybe I should go here and here until you hit the destination that you want. If you hit the destination, then you better actually store where you're going, right? So that you can go back. When you go back, you inform the source, oh, I found an end-to-end route. So if you go this way, this way, this way, this way, you reach. Okay? We cannot afford this mechanism in the network, unfortunately. You can't do that to drive the car, and you can afford to spend hours and hours. But in the network, we cannot afford keeping the source to wait for hours. So what do we do? In the network, we'll say, okay, luckily in the network, we can send multiple cars at the same time. So we'll say, the best way and to guarantee that we will reach to the destination, what do? We flood the network. Okay? When we flood the network, we allow every single node in the network to receive that packet. And the packet itself will keep storing where it's going. Okay? So that if the packet hits the destination, then the packet itself will inform the destination that it has to go through this path in order to go back. Okay? Which what we are referring to here as backward learning. So we know how to go back. So we flood the network and then we know how to go back.
But why would anyone want to do that? The one that you mentioned before, the proactive, is much more efficient, isn't it?
Well, we want to avoid the overhead. We cannot afford this huge amount of overhead. Of course.
But you are getting a lot of overhead by flooding the network. No?
That's once at the beginning, but for DSDV we have to do that periodically. Remember? We have to do that all the time. Here, because if the network has no traffic demands, I'm not doing anything. The network is idle. I don't want to send traffic, and I don't want to exchange any messages.
So you do this for low traffic networks?
Do what?
Reactive protocol.
By low traffic, you mean, yes, I don't get that frequent traffic demands. Yeah, then the answer is yes. But by low traffic, if you mean short sessions, then the answer is no.
No, I mean...
Yeah. If you have short sessions, but they are more frequent, then it's the performance here is so bad, right? So for every single packet you want to send, like short session, the extreme is that you want to send one packet from a source to a destination. You have to establish this route, which means you have to flood. And then after sending the packet, you dismantle everything. You want to send another packet, you have to do the whole thing. So this is good for less frequent, long-term sessions. Okay? The other one is good if the nodes are moving. If the nodes are moving, which means that you have so much dynamics in the network. Okay? And you have short sessions and very frequent type of sessions end-to-end. Which means that whatever you are doing, whatever overhead you're spending, it's not wasted because you have a lot of traffic going from different nodes to different nodes, and this is short traffic, so one packet here, one packet there, but they are very, very frequent.
What if it's less frequent but also dynamically moving? Would the reactive protocol still be efficient?
If it's
less frequent
and
also dynamically moving nodes.
If the nodes are dynamic, this will behave very bad. Will have very bad performance.
But it's less frequent.
Less frequent, but the session is long, right? Mm-hmm. The sessions is long, which means that you have so many packets to send. If the session is long, you send few packets, and then after some times the nodes move. So whatever you have established in the past has become very bad after some time. So either the actual cost of the end-to-end path that you have established 3 seconds ago has increased, or maybe you have no end-to-end connection from that path at all because the nodes are moving. So in general, reactive is not actually efficient for dynamic networks. That's in general. Okay, proactive is good for high mobility networks. or networks with a lot of dynamics. Okay. So dynamic routing protocol, it uses separate route request and reply. So the route request uses what? Flooding. So the route request is sent in a form of flooding to the network. The route reply is sent as what?
Backward learning.
Backward learning based on unicast, based on only sending to a particular path, not broadcast. We do not broadcast the reply. We broadcast the request because we don't know where the destination is. The packets that flood the network, they know where to go, where they are going from point to point. So we'll store in the packet itself where it's going. Just to see this visually, we will talk about the next example. So this example here shows you the steps. If we want to send from node 1 to node 5, node 1 has no idea. There are no tables here. Initially, there are no tables. Not in general, there are no tables. Okay? Not initially. All the time, there are no tables. Okay? So we want to go from 1 to 5. So we will send a packet. This packet will initially have 1 to indicate that I pass through a node 1 through node 1, and then this particular instance of the packet will go to 7. This particular instance of the packet will go to 4. Here, the packet that goes to 4 will increment, will accumulate 4 here to indicate that I pass through 1 and 4. In that order. The instance that went to 7 will say 1 and 7 to indicate that it passed through 1 and then 7. Okay? So this node will receive from here and here, and then this node will forward now here, will forward to from 6 and 7. Remember, I went back. And here we'll send another packet to 4. Okay? So sometimes, just to be efficient, flooding in general, we send to all the forwarding nodes except the node where the packet came from. Which means when I receive a packet from 4, I will flood this packet. I need to send this packet to all the neighboring nodes. Okay? So in that case, I have 1 and 4. I have 4 here. So this packet is coming from 4. So I will forward to all the nodes except 4. Because 4 is where it doesn't make any sense that I receive a packet and I send it back to the...
including 1?
Hmm?
Including 1?
What do you mean?
Like it came from 1 till 4 till 6.
Right. So
6,
4, yeah, 4.
Should not send back to 1 also.
6 does not have any connection with 1.
Ah, right. Okay.
Right? So, yeah, it's like here. When 4 receives the packet, 4 will not send back to 1. 4 will send forward to 6. And 7 will send forward to 2, 3, and 6. But it will not send to 1.
But if it did have a connection, then what?
If 6 has a connection to 1, that's a good point. Then is the packet coming from 1? Only the one that's received from 1 will not go back to 1. But if it's received from 4, I will send it back to 1. If it's received, yes.
If it came from 1 till 4 till 6,
Yes.
will also send back
yes. I send, yes, this is the rule. The flooding, as a rule, I will forward the packet. I always move the packet forward, which means I broadcast it on all the nodes except the one that this packet came from. This is the definition of flooding. only the packet where it came from, or the node that this packet came from, I will not send it back to it. Other than that, I have to forward to all the other nodes. Okay? It's not clear?
No, it's clear, but it's not.
It's a bit strange.
Yeah, like they should have fixed it better.
Uh,
Like if it came from 1 till 4 till 6, 6 shouldn't be allowed to send back to 1 because that would be looping. Then you can get stuck in a loop.
You send from 1 to 4 to 6.
Yeah.
Then I send to from 6. I send to 1.
Yeah. It shouldn't be allowed because it's one of the source. Because then 1 can send to 4 again because they've got it from 6.
Two different processes. 1 to 6 is different from 1 to 6. It's two different processes.
I know that. I'm not saying that it is.
Yeah. So what? No. What she's saying is that instead of looking at the last node number where the packet came from, you should actually look at the entire path.
Yeah. Because then you can just keep going in circles.
If you find that the node that this packet came from exists in the history,
but this packet discovers the route 146. I need to discover the route 16. It's two different routes.
No, he's saying that 146, 6 will send the packet again to 1.
to 1.
I have to discover the new path. 6 to 1 it's a different path.
6 to 1 is a different path.
It came from 1 till 4 till 6.
But
It
remember,
will also
but
send
remember,
back
but
to
yes,
1.
yes, that's right. So there is a packet that's sent from 1 to 6, right? If you have assume that you have here, you have a direct connection from 1 to 6. Okay, then there is a flooded packet that gets sent from 1 to 6.
Yeah.
Right. So this one you will not send back to 1.
Yeah, I know that.
Right.
But that's not what I'm asking.
Right. So when the packet comes from 4, the rule is that you send it to 1 because this is not the node that this packet came from.
Yeah, but then it will keep going in circles. Because now you send 146 and then back to 1. And now 1 received it from 6, so 1 can send it back to 4 again. And then it will keep going 1461.
That's a good
Right.
point. So the packet when it goes back to 1, you will have 1, 4, 6, right?
Then 1 again.
And then 1.
And then 4, 6.
So 1 will now send it to 4 and 7 again,
Yeah.
which means that it will keep going in circles.
Yeah.
That's right.
Is that real? That's how they made. That's how it's designed.
That's
Or maybe they do consider the source.
Floating at the beginning only. Why is it keep sending? And one
right.
send-
If
send-
we're saying that the rule of flooding is that you flood, you send on all the nodes except the node that the packet came from, then
Then this is
but
possible.
one already sent it before to 4. So why the
yeah, but you're checking when you
only
flood.
check the
You
previous.
check the last place only. You don't check the entire path.
That's
What
the
you should do
surprising
is that
thing.
you should check the entire path here to make sure that the packet is not looping. But remember that although this may sound a little bit strange, but there could be some other nodes here. So this packet 1461 will be forwarded to other nodes other than these nodes.
Yeah.
So it will loop. I agree. It will keep looping. But another instance of this packet or this flooded packet will go to different parts of the network. So
Maybe it will just ignore the loops. Since it won't reach to the destination node.
Either you have to have, and what I'm not 100% sure about is that if you check the whole path and check that this packet has come from all these nodes, and then you don't send it back to any of these nodes, I'm not sure if that's an enough condition to visit all the nodes. I'm not 100% sure if that's an enough condition to visit all the nodes or not. It seems that that's an enough condition, but I have to really double check. I have to double check that this is enough. So what you do is that when you forward, you check all the numbers in the packet, and you cannot send to any of the nodes in these numbers. Not just 4 in that case, before and 1. Okay, so if that fulfills the condition that the flooded packet will visit the entire network, then that will definitely prevent the loops. Otherwise, for establishing the route, having loops is not that big of a deal, because let the packet move in loops, that's fine. But once you hit 5, this means that the packet that is going in loops will keep going in loops, that's fine. But this will be an enough guarantee that you will hit 5 no matter what. In which case, once you hit 5, you send a reply back. The reply back will stop all the forwarding, will stop the flooding. You see what I mean? So the loops will stop, all the flooded packets will stop. So that's the thing that you have to be 100% sure that these loops, because as I said, that the packet that will go in loops will go to other parts of the network. So if having loops will guarantee 100% that you hit 5, then have loops. But if we want to prevent the loops during the flooding, then we have to do what you just said. We have to look for all the nodes, and we cannot send back to a node that exists in all these numbers. Okay? So in that case, we will not send to 1, we will not send to 4. And we'll keep doing that. Okay? But does that guarantee 100% hit to 5 or not? That's the question that we need to double check. Okay? So we can double check the routing protocol itself to make sure. For now, we can just agree that we send the flooded packet to all the nodes except the one that it came from. Actually, just to agree on something and move on. Okay. So this way, if you keep doing that, you will hit 5. Once you hit 5, you just need to send the route reply. The route reply will be a unicast, will not be a broadcast, right? And using backward learning, you know exactly your way back from this packet. Okay? Any question? So after you send all your transmission, now you dismantle this route, and when you get another traffic, you do this whole process again and again. The ad hoc on-demand distant vector, this one combines the two. Okay, this is an example for the hybrid category. The ad hoc on-demand distant vector, it establishes the routes on demand, similar to DSR. However, during the establishment of any route based on the demand, you increase your learning about different destinations in the network. This, which is what we have described before. So if you have a network like this, and then based on demands, you'd start flooding, and you have learned through flooding, like DSR. So initially you work DSR, similar to DSR. So you send flooding packets, this is the destination, this is the source, and you have learned through the flooding that the best route is this. Okay? So in that case, start updating, establish a cache or a partial routing table in these nodes, unlike DSR. So the route will get established on demand, but once you establish a route, keep it back in the cache for at least some time. Okay? So when you have another demand from this node to reach to that destination, okay, I will send the flood, right? I will flood. The flooding will reach here, and will reach here. صح? In that case, this node will not flood anymore. Why? Because this node already has a route to D. It will not flood the packet in that case. So you save a lot of overhead by just replying from this node. You reply back to the source or to this node that, okay, stop flooding. I have a direct path to D, so you don't have to keep flooding. So in that case, you use partial flooding on demand, but once you learn something, keep it back in the cache.
But then they don't find the shortest or least distance route.
Well, this node will reply by saying, I have an end-to-end path to D and my cost is X. So this node will decide whether it should go through D, this node, or it should go to any other node, depending on the shortest path. Okay? Because for other parts, you will keep flooding. So if this node tells you that I already have a cost to D, and this cost is X, then you have to decide whether I should keep flooding or I stop flooding. Chances are, by the time you receive the request from this node, you will have received some other replies from partial flooding in other parts of the network. So you will decide whether you should stop flooding and rely on this node to deliver to D, or keep flooding and learn more routes. Okay? So once this node replies, you will take a decision. Whatever I have now, I will decide based on that, which, as you said, it may not be the best path, but this is now a compromise for me to minimize the overhead. Okay? Now I have a trade-off between the time to establish the end-to-end route, right? And whether this route is indeed the best route or not. So, of course, the time to establish the route end-to-end for the case of AODV will be much faster compared to DSR. صح? But I may run into the scenario that because I didn't wait forever for all the flooded packets to come back, maybe the path that I'm taking now is not the best path. Okay? But now I have a trade-off. I now have a trade-off, and this node can decide. So there is another issue here. So of course, the AODV is a very popular routing protocol. This is the most popular routing protocol. That's why it's implemented in NS2. It's implemented in every single implementation about ad hoc networks. The nodes, they maintain routing table instead of source routing. For source routing, they do not establish, or they do not maintain any routing table. This sequence number is added to handle stale cache, which partially solves the problem that you are talking about. That once this node learns a specific route, it will keep it in the cache, okay? Even if nodes move and this route becomes bad and bad, right? The node will keep it in the cache, and this is what we call stale cache. Stale cache yani steady cache. This node does not want to change this route, and it's stuck in the cache.
But update it when it has
Yeah, as long as there is traffic going on, this cache will keep there.
But update the cost of the path with dynamic change. Or
Not regular. There's no regular updates here. There's no regular updates. So the cost will get stuck in the cache. But what happens here? Remember, there is partial flooding that happens. So if this node, there may be a situation based on which that this node will receive another message update, another flooded packet to D from other parts of the network. So in that case, this node will now have to perform a careful procedure, a smart procedure. If this packet tells this node that my route to D is fresh, then this node will give away the route in the cache and will store the new one. The freshness of that route is measured by what we call sequence number. So the sequence number measures the freshness of the route. Because if we do not use any indication that this is a new route or this is an old route, this node, once it receives any route update, any flooded packet from anywhere, it will stop. It will stop and say, whatever I have in the cache will do. So that's it. I will not update my my route in the table, and I will stop the process up to this point. But if the sequence number tells it that this route is fresher, then this node will accept it and will put it in the table in that case. So this sequence number measures the freshness of the route. Okay. So of course nodes remember from where a packet came and populate the routing tables with that information. That's what we talked about in that each node will maintain a routing table which is definitely different from DSR in that case. And this will save us to flood the network with a lot of packets, whereas we already know how to get to the destinations, so we don't need this information. So now we talked about three different routing protocols in three different categories. One is proactive, one is reactive, and one, which is the most common routing protocol, which is AODV. So optimal routing protocol for wireless mesh networks must capture the following feature. This is the metric. The issue now is that we know how to calculate the path end to end, but the question is now, how do you calculate the cost on each link? Well, the cost may be 1, which means that if you go through a street, this is 1 hop. So the simplest way of estimating the cost on any link is by saying that this is 1 link, 2 links, 3 links, so number of hops. So if I want to go from my house to the university, regardless of how lengthy the street is, I will count it as 1 street, 2 streets, 3 streets, and that's it. And of course, this is not efficient. So there are multiple ways to calculate the metric. The metric is actually, it estimates the cost that you have to pay in order to send one packet on this link. So for example, when a link on a minimum hop count معناه ايه؟ This is the minimum number of links end to end. So simply in a network like this, if I want to get to this, from this source to this destination, I will be forced to go this way, because this is 1, 2 hops, that's it. Any other node will lead to a more number of hops. But is this actually the best path? Not necessarily, because this node or this link might be very congested. The channel on this link might be very bad. So in that case, this path may not be the best path. Other ways of calculating this metric are by measuring what we call the link quality. Okay, so the link quality can be measured by what we say round trip time. Round trip time is basically the time that the packet takes to be sent to the next node and come back. So for any 2 nodes, we send 1 probe, and then this probe will be sent back. We calculate this round trip time, and this is what we call a round trip time. So the quality of the link is measured by what we call round trip time. So as this link is shorter and faster and the channel condition is good, this round trip time will be less and less, which indicates that the cost of sending a packet on this link will be less. So that's a good link. Okay? So that's one way of measuring the link quality. So it's better, it's definitely better than the number of hops. But now I have to do some measurements. This is different from the routing messages. I have to do measurement for the round trip time in order to calculate the metric. So that's one thing that has to be considered for any routing protocol. Another issue is what we call scalability. So first, I have to do certain measurement if I want to measure the link metric or the quality of the link. I have to do some measurements. Scalability is another factor, that setting up a routing path in a very large network is actually very costly. Imagine that we have to do this flooding on a very, very large network. See the amount of packets that have to go back and forth. Even for the case of proactive, I have to exchange a huge amount of packets, even if there is no traffic going on. So the scalability is another issue. So the AODV seems to be the most scalable because it addresses some trade-off. It tries to minimize the overhead, and at the same time, it creates the end-to-end route faster. So it's kind of a trade-off between being proactive and being completely reactive. And through simulation, and that could be a good assignment or a good exercise, is to calculate the establishment of the end-to-end route for the case of AODV, and the case of DSDV, and the case of DSR, as the network grows large. Okay? Of course, in normal cases, DSDV will be much faster in establishing the route, but that requires a huge amount of overhead at the beginning. Which at the beginning, all the time, it requires a huge amount of overhead. The DSR will take forever to establish the route end-to-end. But because of no overhead in terms of, regular overhead, it doesn't send any regular route updates. Once you establish the route, which takes a very long time, you can send your traffic smoothly, unless the nodes are moving. So now, if you have so much dynamics and the network is growing large, it's proven through simulation that AODV is the most scalable. Okay? So it's very critical to have this scalable routing protocol. Robustness is, by robustness here we mean that the routing protocol is tolerable to failures. If there are some failures, the routing protocol will keep you alive, will keep you operational. That's what robustness means. So to avoid service disruption, so for example, DSR is the worst in terms of robustness. Why? Because you spend some time to establish the route, and then if one of the links is down or one node moves, tough luck, you have to repeat the whole process again. DSDV, on the other side, can tolerate some failures. Why? Because you always update the nodes, you always update the state of the link. So even if the nodes are moving, even if one node is down, you always have snapshot information from multiple nodes that tells you, okay, that this node is alive, this node is dead, something like that. So regular updates will keep you up to date all the time. So this is another issue. So the issue of the metric, one way of measuring the metric between two nodes. So we talked about the round trip time, right? So the round trip time is measured by simply sending a probe from A to B, and then B will forward the probe back, and then A knows when it sent the probe, when it received it, it subtracts this timestamp from this timestamp, it knows the round trip time. That's easy. But is the round trip time the best way to calculate the link quality? It turns out no. Why? Because round trip time calculates the time that A sent the probe to B, right? If B here is very busy, it's loaded by so many things, what will it do? It will not send back the probe right away. it will queue this probe, and then it will send it when B is not busy. Which means that this round trip time now is the propagation time plus the queuing time plus the propagation time on the way back. So it's not the link quality, it's the link quality plus some other time that's spent on B. And this queuing time on B now is variable. It's not related to how the link condition is. In other words, round trip time is not necessarily the best way to calculate the link quality, because it may lump sum some other factors with the round trip time.
Do these probes affect like actual data packets that the nodes might be receiving? Because I remember
They shouldn't.
I remember before, like last week or before that, you mentioned that the receiving node cannot receive a packet if someone else is trying to send to it. If another node is trying to send
you
to
have
it.
This right? This is from the MAC layer.
Is that not related here?
The MAC layer is something in the lower layer. Now we assume that this probe will be sent. When this probe is sent from the routing layer, we actually use some kind of a reliable MAC layer protocol, which means that if this probe is not sent properly from the MAC layer, this node from the MAC layer will retransmit. Okay, and this will happen here for the expected number of count here. We'll talk about that.
It does affect the time.
It does affect the round trip time for sure.
Even the MAC layer.
Oh yes, of course.
Okay.
We are very much dependent on the MAC layer. No matter what you do, you are very much dependent on the MAC layer here. So any retransmission, anything will be affected, will be calculated in the round trip time, and it should, because this is in a way related to how good the channel is, right? Because the channel has a certain probability that the packet may get lost. The channel is bad at this point in time, so the packet got lost. So this should be part of the round trip time. So another, so as we said, round trip time may not be the best way. And there is a paper here, which I will probably post on Blackboard, that gives you the routing protocol performance as a result of using some of these metrics to see how the throughput will look like at the end if we use this metric or we use, of course, hop count is the worst. The hop count is the worst. We agree on that. It's natural. But is round trip time the best? We call it per hop round trip time, which means that for every link, for every 2 nodes, we'll have to do that. Or what we call expected transmission count. How do we calculate the expected transmission count? That's a little bit complicated. So what happens is that in a specific duration of time, we send from A to B, we send n probes. So it's not one probe in that case. We need statistical way of calculating the expected number of time that we need to transmit any packet from A to B. Okay? And that will give us an indication about the quality of the link. As you mentioned, if we try to send a packet MAC layer from the MAC layer, it does not reach to B in one single time. It may be 2, maybe 3. Okay? So depending on that, expected number of transmissions, we can get some indication about the link quality. It turns out this metric is actually more accurate than the round trip time. Okay? So how do we calculate this? Well, let's see. A sends n probes to B. B will then send the n probes back to A. A, from the n probes, B received n1 probes. So for example, I sent 10 probes, 9 of them reached B. So what is the probability from A to B? What is the probability of success? Probabilities, huh? What is the probability of success? 9 out of 10.
90%.
Yeah, so 90%, right? So when B sent to A, unfortunately, only 8 probes. So the probability is 80%. Okay? So we assume that for sending any request or any message from A to B, B has to send a reply back. So what is the probability of success on this link? What is the probability of success on the link? The probability of success on this link is the fact that if we send a packet, the node has to be successful in reaching B, okay, and the reply has to be successful to reach back to A. Okay, and means what? Means the probabilities are what? You forgot everything about probabilities?
What?
Yes.
What?
Probabilities. You have to refresh your memories about probabilities.
Oh, really?
Yes, unfortunately.
Great.
Okay. So the probability
That means they are correlated.
probability from A to B تساوي the probability from A to B and B to A. And means in probabilities multiplication. So times the probability from B to A. Which means that if it fails on any of these lengths, on any direction, this means that the packet fails. Okay? So in order to send a packet successfully from A to B, it has to be successful from A to B, and then the reply back has to be successful from B to A. If that's difficult for you, then you should really seriously think about refreshing probabilities, because what's coming is a little bit more complicated than this. So the probability of sending one single packet, this is the probability of success. This is the probability from A to B given that the packet is successful. This equals what? N1 divided by N multiplied by N2 divided by N. I don't care about this, just call this P. This is probability of success. This is the probability of success for one single packet. Is this what we...
The lower N is the number of times you've sent?
The number of probes you sent, all the total number of probes,
yeah.
right?
Okay.
And the N1 is the ones that
From A
that
to B.
is the ones that, yes, that were received successfully. The one that actually reached B. Because not all of them. If all of them reach B, then the probability is 1.
Okay.
right? N over N is 1. That's fine. Okay? So this is the probability for one single packet. Is this what we want? The expected number of transmissions from A to B is what we want. We want the expected number of transmissions. Which means that we want to send a packet from A to B. It may reach B from the first time. صح? Or it may reach B the second time. Or it may reach B the third time. Or the fourth time. Or 1,000 after 1,000 times. صح? So a packet, this count is a random variable now. So the expected number of transmission is a random variable, which could take the value of 1, 2, 3, 4, 5, 6, 7, we don't know. Okay? So then the expected number of transmission is a random variable. It's not as simple as round trip time. Round trip time is easy. Send probe, you get it back, calculate the time, that's it. Unfortunately, this one is not that easy. So the expected number of transmission is a random variable. So the way we deal with random variable, in order to get the expectation of any random variable, do we know how to do that? So, okay. So that's the first thing. So the probability of being successful from the first time is this. So the probability of x is the random variable, which indicates that we have a successful transmission. What is the probability that x equal 1? This equals to the fact that we send the packet one time and it gets to B. What is that probability? What is the probability of success from the first time? صح كده؟ اللي هي P. Now we called it P. صح? Okay. What is the probability x equal to? No, probabilities are very, very interesting, by the way, and just this is a very extremely powerful tool to really get good analysis about any problem that you're investigating. It really makes your research work a lot more interesting. Okay. So what is the probability that x equal to? This means that we have to send the packet 2 times. This means what? That we send it the first time and it fails. Then we send it the second time and it succeeds. صح? Because if we send it from one time and it succeeds, then this x equal 1. Okay? So x equal 2, this means that we send it the first time and it fails. What is the probability that the packet fails?
That the packet fails the
Fails.
second time?
No, fails the first time. The probability that the packet succeeds is P. The summation of the probabilities is always 1.
So 50%.
Right? Not 50%. It doesn't. It's 1 minus P, whatever P is. We said that P is the probability that the packet succeeds on the link. Right? So the probability that the packet fails, because it either succeeds or fails. We send the packet, it either succeeds or fails, right? We know that the probability that it succeeds is P. So the probability that it does not succeed is A, 1 minus P. Probabilities always have to be 1. The total probabilities always have to be 1. What are, in other words, we can calculate it in a different way. What are the possibilities that the packet fails? Well, we send it and it fails on the way forward to B. Okay? But it succeeds from B to A. But we don't care because it fails on the forward direction, so for us it fails. Or maybe it succeeds on the way to B, but it fails from B to A. That's also failure, right? Or it fails on both. That's also failure. The summation of probabilities of all the different combinations is 1, which means that the probability that it succeeds is only one possibility. It has to be successful on the way forward and successful on the way backward. Other than that, it fails. Talama, as long as we said other than that, this means 1 minus P. Because the summation of all probabilities is 1. Right? So the probability of success is P. So the probability of failure is anything else. Anything else means 1 minus P. Okay? So x equal to is the probability that it fails the first time, and then the second time it succeeds. What is the probability that it succeeds? P. صح? It's getting too difficult, huh? Actually, يعني, if you review any basic probability material, this will be a piece of cake. Yeah.
Okay.
So the probability that it fails in the first time is 1 minus P. The probability that it fails in any time is 1 minus P. The probability that it succeeds is P. That's as easy as that. So x equal to معناها it fails the first time and then it succeeds. Fails the first time 1 minus P, and it succeeds the second time is P. What is the probability that x equals 3? This means that it fails the first time, it fails the second time, it succeeds the third time. And. Okay? Which means that 1 minus P multiplied by 1 minus P multiplied by P. Okay? So in other words, the probability that x equal any n is what? Is 1 minus P to the power what?
N minus 1.
N minus 1 multiplied by P. Okay? This is the probability. So now we have a random variable that takes the values 1, 2, 3, 4, n. Okay? And we know the probability of each single case. How do you get the expectation? Average, which is how? So
Sorry, what was the question again?
we have a random variable now. It takes the values 1, 2, 3, 4, and so on. And we know the probability of every single case. Now we want to get to the expectation. The expectation is what? The expectation tells you on the average, based on this P, the probabilities, on the average, statistically, the expected value for this random variable will be this. Okay, how do we do that? In probabilities, this expected value is simply The expected value for any random variable is basically, this is the expected value of x equals, for all possible values of x, all possible values, so x takes 1, 2, 3, 4, whatever. So x equals I. And I is 1, 2, 3, 4, 5. And I can take any value from 1 to infinity. We don't know. Okay? I multiplied by the probability of I. What is the probability that x takes the value I? This is 1 minus p, I minus 1, multiplied by p. Okay? So this is the average, as Ala said, but the average refers to the fact that you have multiple values and the probability of taking these values is equal. But unfortunately here the probabilities are not equal, so we have to multiply by the probability. So each value has to be multiplied by, because it makes sense, the probability that x equal 2 is less. So as the more trials, I mean, otherwise it's so bad. Yani. So the expectation, if it's 2 or 3, the probability decays, which means that the probability of that x equal 1 is higher, right? Otherwise the link is so bad. Yani. But we have to calculate it statistically. So what is this summation? So now it's algebra. Now it's algebra. So now we finished probabilities, now we're switching to algebra. So what is this summation? How do we calculate this summation? Well, this summation, we have to look at it. It's a little bit complicated. Why? Because it's no, this is the limit. Okay, but in other words, for any infinite series like this, we know how to get the summation for an infinite series if it's a geometric series. يعني geometric series, the geometric series that's مثلا ايه geometric example of geometric series is r to the power I. And I is 1, 2, 3, 4, which means that every time we multiply by r. If you go back to algebra, the basic course about algebra, the summation of r to the power I from I equal 0 to infinity, that's so easy because this is equal 1 over 1 minus r. We know that. That's a fact. We know it. And we can prove it easily. I can prove it to you easily. But this is what we call a geometric series. Geometric series is like you start with a number. It could be here any يعني we can have here any constant number, C مثلا. C or A, but this is a constant number. You start with any constant number. Okay? And then you multiply R. And then you multiply R. Subject to the fact that R has to be a less than 1. معناها this number will be decaying. Right? We know how to calculate this summation as an infinite series. We know. Because it's decaying. Right? So it's easy. We know how to do that. And the summation is a C over 1 minus R. So that's a fact. We know that from basic algebra course. We know that. But if we look at this series now, unfortunately it's not a geometric series. Why? Because of this I here. I takes the value of 1, 2, 3, 4. It's not a geometric series. If this I is constant, then it's a geometric series. But unfortunately, it's not constant. Because you have I here and you have I at the exponent. If you have a series that's 1, 2, 3, we call this a sequential series. It's not geometric series. We know how to calculate the summation for sequential series, and we know how to get the summation for geometric series, but we don't know how to get the summation of a mix of the two. Okay? So I don't know. Should we go through that? It's very easy, but should we go through it? Well, and we'll stop here, and because I feel that you have يعني you started to feel it's
Well, are we gonna have to like solve problems like this?
not solve problem, but you need to understand how can we calculate the expected number of transmission time.
I'm following so far.
You're following? Okay,
Yeah.
that's good. Okay, so that's what we need to know. You don't have to know anything more than that. So you know how we prove it until now, at least, because we did not talk about what is this summation look like. Okay, and I feel that we have gone over time, so we could stop here, or we could just talk about the proof. What do you prefer? Because we have to go through your presentation quickly.
As you wish.
Okay.
It's up to you.
Okay. What do you feel? Stop here.
شو اصلا قلنا اصلا نثبت بعد كده البروف ده وصل للقانون ازاي؟
Yep. ماشي. Okay. So we can stop here.